Light is indispensable for life, yet UV rays from the sun constantly damage DNA. I'm Bern Kohler, Professor of Chemistry in the Department of Chemistry and Biochemistry at Montana State University in Bozeman, Montana. I'm pleased to have a few minutes to discuss with you our research described recently in a perspective article I wrote that appeared in the Journal of Physical Chemistry Letters and entitled Non-Radiative Decay Mechanisms in DNA Model Systems. DNA absorbs ultraviolet light very strongly, producing excited electronic states that contain a great deal of energy. This energy occasionally leads to damaging photoproducts that can alter the information encoded by the genome, leading to diseases, including skin cancer. Fortunately, the quantum yields of photochemical damage are kept very, very low due to remarkable photophysical deactivation pathways, especially non-radiative decay, that are just now coming into focus. Excited states of monomeric DNA bases are remarkably short-lived. In less than 1 picosecond, in other words, in just hundreds of femtoseconds, excited DNA bases return non-radiatively to the electronic ground state. This is the same functionality found in molecules that work as sunscreens. In order to study these very rapid events, we use femtosecond laser spectroscopy.
To run our transient absorption experiments, we take the output of our titanium sapphire femtosecond laser and split it into two parts. A high energy part that we use to frequency triple to generate our UV excitation pulses, and a smaller energy part that goes down an optical delay line to delay the pulse in time relative to the excitation pulse. The excitation pulse prepares our molecular excited states. The probe pulse follows in time to determine the fate of those excited states.
DNA bases and oligomers are dissolved in aqueous solution, which is held in this little spin cell. Our pump and probe beam will overlap in this cell to generate our excited state of DNA and also let us observe the excited state dynamics.
Non-radiative deactivation helps to keep DNA bases from undergoing damaging photochemical reactions, thereby safeguarding the genome. Non-radiative decay is really all about a non-reaction, returning a molecule safely back to the electronic ground state, as opposed to changing its chemical identity through a photoreaction. It makes sense then to think about these events in the same terms a chemist would use to think about reaction dynamics. In a photochemical reaction, nuclear motions define a pathway that move a molecule from reactant to product via a transition state. In photophysical decay, the path returns on itself, bringing a molecule back to its starting point. In fact, it's a lot like hiking in the mountains. The whole point of hiking is to return at the end of the day to your starting point. So what are the kinetics, what are the timescales, and the pathways or nuclear motions responsible for bringing us from an excited electronic state safely back to the electronic ground state? A Jablonski diagram summarizes the kinetic events that link excited states. There are straight lines representing radiative transitions of absorption and fluorescence, and wavy ones that denote non-radiative steps. Non-radiative decay may occur via so-called dark states that are not reached by photon absorption. To get another perspective on non-radiative decay, we're going next to the Bridger Ridge, high above the Bridger Bowl ski area. A ski area is a great place to think about Jablonski diagrams. There are straight lines or chairlifts that bring skiers or hikers to a high energy state, and wavy lines that show how they return to the base. Frequently, it's possible to descend via another peak that's not served by any lift. Perhaps DNA is a bit like a well-designed ski mountain, where most trails lead back to the bottom, and getting lost is difficult. I'm standing now on top of the famous Bridger Ridge, high above the Bridger Bowl ski area. We've come up about 2,500 feet, a little more than 700 meters from where we parked our car. And the potential energy gain of One of my DNA molecules, which has a mass of about 3 picograms, is very considerable. It took me an hour and 40 minutes to get to this point, and yet the same amount of energy is deposited in that same DNA molecule by UV light in less than a minute. Because the lift won't be running anytime soon, we're going to follow the non-radiative pathway, hopefully back down to our car at the bottom. While ultra-fast laser experiments can measure how long it takes, computational chemistry is needed to precisely map the paths that lead downhill. These studies indicate that non-planar deformations are particularly effective for bringing a molecule to the conical intersection responsible for non-radiative decay. For the DNA bases, as on our mountain, multiple pathways are present and bifurcation dynamics is commonly observed due to the presence of multiple pathways. Much as a skier can easily find a path that is entirely downhill with no climbing, the potential energy landscapes for the DNA bases predispose them for rapid, all-downhill journeys back to their starting points. Quite surprisingly, excited electronic states in so-called DNA-based multimers, such as a DNA oligonucleotide or a DNA polynucleotide, a system that contains 2 or more nucleobases, can occur much more slowly than in the monomeric systems. Understanding this non-radiative decay has been a tremendous challenge in the past several years, with competing explanations being advanced by researchers from around the world. Indeed, this constitutes one of the most active and exciting frontiers in this research field today. With so many trails yet to discover, the future of DNA photophysics is bright indeed.